In the southeast of Berlin in Adlershof, the Helmholtz-Zentrum Berlin operates BESSY II, a particle accelerator which produces extremely bright X-ray light. BESSY II is the only German synchrotron radiation source that generates this so-called soft X-ray light, which is why researchers from all over the world come to Berlin for their studies at Helmholtz-Zentrum. One of them is Dr. Tristan Petit, who uses BESSY II for his prize-winning studies on new materials for storing electrical energy.
So I'm working on a new class of material called MXenes, which are very interesting for new type of energy storage system. And especially I'm using the synchrotron BESSY II to try to understand how energy can be stored in such materials.
But how does the particle accelerator work? BESSY II is both an X-ray microscope and a slow-motion camera. In the middle, you can see the so-called synchrotron that accelerates electrons to almost the speed of light. On the outside is the electron storage ring with recurring magnetic zones. When the electrons pass through these, the X-ray flashes needed for research are created.
We use these X-rays either to analyze the chemistry of a material or the structure of such materials. And for that, there are different techniques available which are sitting around this big ring where we are measuring a few times per year. My research is basically an example of what we can do with the light that comes out from BESSY and how we can use it to understand problems that are relevant for many users from all around the world are coming to measure. In my case, I usually work through collaboration, so I have collaborators who send me samples and we analyze their samples with the techniques we are developing here.
Round about 2,000 scientists like Tristan Petit come to BESSY II each year. At the various beamlines in the experimental hall, they can do their research using the brilliant light the particle accelerator offers.
So the use of this X-ray makes the method very particular. For example, in my case, I was looking with battery materials which may have a lot of different elements, and using X-ray we can look at each of these elements separately and analyze, for example, only oxygen atoms, only titanium atoms, and this is not possible with other techniques than X-ray spectroscopy.
With the help of BESSY II, Dr. Petit is researching the new material group MXenes. They can store and deliver large amounts of electrical energy extremely quickly and therefore might play an important role in future energy storage, especially in the context of renewable energy.
We want to see inside this particle chemical reaction happening during charging and discharging, like in a small battery system. So this is very challenging because we have to probe the different atoms, and we also have to focus the X-ray over a very tiny very tiny space. So especially this particle are a few microns, and using X-ray microscopy, we can focus the X-ray over a few tens of nanometer, which is extremely small. So the biggest challenge is combining this X-ray microscopy techniques, which have not been done for liquid measurement, into a cell which simulates a real battery environment. And this has to be done in liquid. And these two worlds of X-ray microscopy, which works in vacuum, and of a battery which works in an electrolyte, so which can be water or another type of electrolyte, is very challenging and hasn't been done so much. So what I hope is that thanks to my research, we may understand better how this material could be a game changer in the battery world. And hopefully in 10 years from now, there would be such new materials in every battery that we have around. And I would hope that my techniques contributed a little to this development.
On November 2nd, Ingo Müller from the Helmholtz-Zentrum Berlin will virtually present the particle accelerator in German. Afterwards, there will be a Q&A session.